Hello dear students, in the continuation of the solution of multiple choice questions based on magnetic effect of current, let us solve some more multiple choice questions. The first question is, the magnetic field in a certain region of space is given by B vector is equal to 8.35 into 10 to minus 2 I unit vector Tesla. A proton is shot into the field with velocity v vector is equal to 2I unit vector plus 4j unit vector into 10 to power 5 meter per second. The proton follows a helical path in the field. The distance moved by the proton in one complete revolution in helical path in YZ plane will be. These are the options. So, solution to question 1. As the velocity of proton moving in the uniform magnetic field has both the horizontal and vertical components, therefore it will move on a helical path, and we know this is helical path. Distance traveled in one complete revolution is known as pitch, which is equal to the time period into horizontal velocity. Distance moved in one complete revolution in the helical path is equal to pitch, which is time period into horizontal component u cos theta. Here t is time period, which is 2 pi m upon magnetic field into charge, into u cos theta is 2 into 10 to power 5, 2 into 10 to power 5, which on simplification gives 2 pi m is 1.67 to 10 to minus 27 into 2 into 10 to power 5 upon b 8.35 into 10 to minus 2. E is charge of proton 1.6 into 10 to minus 19. On simplification it gives 0.157 meter. So the correct option will be C. This is the helical path. And this is distance, horizontal distance moved in one complete revolution, which is called pitch. Now second question. A long straight wire of radius A carries a steady current I. The current is uniformly distributed over the cross section. The ratio of the magnetic field B1 and B2 at the radial distances A by 2 and 2A respectively from the axis of wire will be. These are the options. So, solution to question 2. From Ampere's circuital law, line integral of B dl is equal to mu naught times total I enclosed by the closed curve. So, for inner concentric loop of radius A by 2, line integral of B1 dl mu naught I upon pi a square into pi a by 2 square means pi a square by 4. So, B1 into 2 pi a by 2 will be equal to pi a square cancels out and mu naught I upon 4. Here 2 also cancels out, so B1 will be equal to mu naught I upon 4 pi a. Suppose this is equation 1. Similarly, for outer loop of radius 2a, Ampere's law gives B2 dl is equal to mu naught times sigma I, which is B2, into dl is 2 pi into 2a is equal to mu naught into I, because I is the total current enclosed by this closed loop of radius 2a, which gives B2 as mu naught I upon 4 pi a. Thus, suppose this is equation 1. From equations 1 and 2, we get B1 upon B2 is equal to mu naught I upon 4a upon mu naught I upon 4a means 1. Mu naught I upon 4 pi a upon mu naught I upon 4 pi a, which gives 1. So the correct option will be A. Next question number 3. The question is, in the diagram, I1 and I2 are the currents in the loop and straight conductor respectively. OA is equal to OB is equal to R. If the net magnetic field at center O is 0, then I1 upon I2 is, these are the options. So, solution to question 3. Here, this is circular current loop of radius R and carrying current I1, and this is a straight wire carrying current I2. OA is equal to AB is equal to R. So the distance of wire from center O will be 2R. Now, according to question, at center O, B1 minus B2 is 0, where B1 is the magnetic field is due to loop, and B2 is magnetic field due to wire. This means that B1 loop is equal to B2 wire, and we know magnetic field due to circular current loop is mu naught I. So mu naught I1 upon 2 into radius will be equal to mu naught I2, magnetic field due to wire at perpendicular distance. R plus R means 2R will be mu naught I2 upon 2 pi into 2R. So mu naught upon 2 cancels out, and we get I1 upon I2 equal to R also cancels out, and we get I1 upon I2 is equal to 1 upon 2 pi. So the correct option will be C. Now next question number 4. The question is, a square loop ABCD carrying a current I is placed near and coplanar with the long straight wire XY carrying current I. The net force on the loop will be. Here this is a square loop of length L of each side and carrying current small I. This is placed coplanar with a long straight wire XY which is carrying current I. The distance of side AB is L by 2 from the wire. Then we have to find the net force on the loop. Solution to question 4. Because current small I in side AB and current I in the wire are parallel, therefore the force between wire and this side will be attractive. So net force will be equal to attractive force on side AB, FAB, which is attractive because this current and this current are in the same direction, and this current and this current both are opposite to each other, therefore the force will be repulsive. So F on CD will be repulsive. Now values will be mu naught I upon 2 pi into this distance this force will be magnetic field due to this wire B1 into I into L minus magnetic force, magnetic field due to this wire here B2 I into L. Now B1 will be equal to mu naught I upon 2 pi into this distance L by 2 into I into L minus B2 is mu naught I upon 2 pi into this distance means 3 by 2 L into I into L. On simplification it gives mu naught I upon mu naught I upon pi minus mu naught I upon 3 pi so mu naught I upon pi may be taken common, I get 1 minus 1 by 3, so it will give 2 by 3 mu naught I upon pi. So the correct option will be D. Next question number 5. The question is, a metal rod of mass per unit length 0.5 kg per meter is lying horizontally on a smooth inclined plane which makes angle 30 degree with the horizontal. The rod is not allowed to fall by passing a current through it. When the magnetic field of 0.25 Tesla is acting vertically upwards, the current in the rod will be, these are the options. Now, to understand the question, suppose this is rod carrying current I in this direction. Its length is L and mass per unit length is given to be 0.5 kg per meter. The rod is lying in equilibrium on the inclined plane which makes angle 30 degree with the horizontal. Magnetic field B of value 0.25 Tesla is acting vertically upwards. Clearly the rod will be in equilibrium if the component of its weight mg sin theta down the inclined plane will be equal to the magnetic force BIL cos theta of the inclined plane. So, for equilibrium, the magnetic force of the inclined plane must balance the component of weight down the inclined plane thus mg sin theta is the component of weight mg down the inclined plane, whereas BIL cos theta is the component of magnetic force of the inclined plane. When these two are equal and opposite, then the resultant force on the rod will be 0 and it will be in equilibrium. Thus, mg sin theta will be equal to BIL cos theta, which gives I as mg sin theta upon BL cos theta, m upon L into g by b. Sin theta upon cos theta gives tan theta. So, I will be equal to mass per unit length is 0.5, G is 9.8, B is 0.25 and tan theta is tan 30. So, we get current as 11.32 ampere. So, the correct option will be A.